So good morning, everyone. My idea to present here the SATO platform concept and architecture is to provide a basis for most of the presentations that come later. Just to have a brief overview, as Pedro was mentioning, the idea of SATO project was to create an IT platform for the automated self-assessment and self-optimization of energy. And the idea here is to provide real-life building energy use smartness and occupancy. Our approach was based on using a lot of semantic-based interoperability to integrate various heterogeneous data and systems that we had in our partner buildings. The general idea of this platform is that we have we developed a cloud-based platform that will integrate several cloud and platforms that existing in the buildings. And then also integrate with several external data sources from the internet. And we are employing, to develop this platform, we are employing enterprise level software that is widely used in the industry, not trying to create new software from scratch. And we are implementing this platform in a way that is agnostic on the computing platform it is running. So we can run in our on-premises infrastructures, or also we can deploy exactly the same platform in a public cloud infrastructure. So we have been relying strongly in standardized data models and interface to represent and implement these modeling concepts around the buildings and the buildings. So we have focused on creating, using the semantic models that exist and extending them to our needs to better accommodate this self part of the project on trying to do autonomously stuff there regarding the obtaining data, calculating KPIs, calculating assessments, and then executing optimization. We have been using several standardized semantic models for devices, building, and other entities involved in this process. Our approach for creating this platform was to create a top-down approach to integrate the SATO platform first with its ecosystem around. So we have actors, external data source, and the buildings. And internally, we foresee the three main divisions of components from this architecture. We have a middleware that is responsible for ingesting the data, providing the semantic interoperability, the syntactic interoperability, and migrating from this raw data storage to a more refined storage where data is more harmonized. Then we have the middle layer, which is the self-assessment framework, which is basically the main brain part of the architecture that computes most of KPIs, provides a result storage, and then uses also this building and assessment semantics. And in the top layer, we have the intelligence parts that will use those assessments and KPI to take decisions on what should be done to improve the energy management of the building. It's not expected to see everything there. It's just to show more or less how we organize this architecture. We have created more than 25 components spread across these three layers. Many of them deal with the semantic standardization here at the bottom and data preparation for the assessments. Part of storage data, and then also the processing KPIs, calculating assessments, and everything else. Here we have both self-optimization services that will use these assessments, and also user interface to provide ways of the actors acting directly upon the building. So basically this infrastructure focuses on trying to be the most autonomous as possible, or providing the most information as possible for building managers to take informed decisions on how to improve the energy management of this building. From these 25 conceptual components, actually, we have implemented more than 107 real components. We have several different platforms that we are integrating in the buildings. Then we have several aspects for preparing the data, storage in different structures, and so on. And here we have several different examples of assessments that we are doing in our platform, which will be the topic of many of the following presentations from this one. Just to conclude, these are conceptual components that implemented the default vision of each one of these components, but of course, we have multiple pilots, multiple buildings, and each building may launch or may instantiate several instances of each one of them. So we end up having, from those 117 components, spreading out into other hundreds of computing instances for calculating all of that. So just to have a few numbers on the current state of the SATO platform that is running today, we have 9 pilots, more than 80 buildings. Of course, these 8 buildings, we are counting each residential home as a building here conceptually. We have more than 450 registered spaces and zones in those buildings, and more than 3,000 devices already connected with our platform, sending data, receiving actuations, and so on. From those, in a snapshot we took from the platform, we had already running at that time 134 KPI instances, so they were calculating at that time, and 104 assessment instances. Our platform, the core of our platform already contains more than 26,000 lines of code for preparing the configurations and deploying all the architecture in an infrastructure. And if we focus only on the line of codes for implementing those assessments, KPIs, and everything else, we have more than 11,000 lines nowadays. So this is an overview of the current status of the platform, focusing again, once more, in the self part and being dynamic as the environment changes. We contextualize that and take profit from this to change also our platform. So with this, I finish my presentation, and my colleagues will present several of these examples of assessments, KPIs that we are using in this platform. So thank you.
So thank you. The questions, we are doing these 4. Okay, okay. All right. So we do these 4 presentations now about the overview of the project, and we get questions after it. So now I will present Per Heiselberg, a full professor from the University of Aalborg. You will have the presentation on the second layer that you saw in the architecture, the self-assessment framework.
Thank you very much, Pedro. Yes. I'm going to present the brain or the heart or whatever we call it. At least it's sure that if the assessment doesn't work, the platform is not alive, so you can discuss what part it is. But what is the self-assessment framework? We have created a library of a number of parameter and system identification methods. And these are actually the ones we are using in this self-assessment and optimization. And I will, in this presentation, go through some of the different, you could say, type of assessments and scales we have included. Of course, we cannot go into detail with the different assessments because I think the library includes around 130 parameter and system identification methods and around 90 key performance indicators. So I will just give you an idea about what are the types of assessments, how do we characterize them, what can they do, and so on. And then just give you one example. We have assessments, of course, for the different aspects of buildings. So this, and we have divided it into these different categories. So we have the energy conversion technologies, heat pumps, boilers, solar thermal systems. We have the energy distribution systems in buildings, heating, cooling, ventilation, distribution systems. We also have different kinds of energy storage in the building that we are characterizing and assessing the performance of. Then, this is the system side. Then, of course, you also have the building side. where we're looking into what is the energy use and the performance in different spaces, rooms, in different zones and buildings, and how do different appliances included in the buildings perform. But we also have a few assessments looking into the building envelope, how do the window opening, shading, and so on perform in the building. So we have characterized these different assessments in different parts of the building. Then we also have looked into how we can, you could say, distinguish between what the assessments actually do. So this means we have different kinds of levels of resolution. So we have a resolution based on the geometry. So we have some assessments which are focusing on the performance of the room, of the zone, or of the whole building. And we also have a system-based resolution where we go from assessing individual components to assessing subsystems and whole systems. And of course, the requirements you need, and this is usually the data requirements you need, is of course very different if you want to estimate the energy use of a whole building or you want to estimate the performance of a fan. So therefore, we are quite dependent on what is the level of data available in the building. And if you look at the building stock, the level of data is very different. You could say the lowest level we are working with is what we call level 1 billing. This means you probably only have energy meters for the whole building. And of course, this gives some possibilities to assess the performance compared to what you expect it to be. You can analyze it in a time series and see, does it work as it is expected? Does it work better today than yesterday, and so on. So of course it does give you some opportunities, but it's on a relatively high level. Then we have another level which we call where we have the possibility to investigate not only for the whole building, but actually also what is going on in several systems. This is typically what we have in our building regulations. So newer buildings, there is a requirement that you monitor energy use for ventilation systems. You may monitor energy use for other components in the system. That is a requirement. So this means we have a higher level of data availability. Then level 3 is where we also have a possibility to evaluate what is the you could say outcome of our systems. What is the quality of the indoor environment? So this means we can not only estimate performance of systems, but we can actually also evaluate if they achieve the goals that we expect them to do. So this means we can also see for certain energy performance, do we actually achieve what we want? And then the highest level of data availability is when we also have data available on individual components in the systems. So this can be, we have energy use for a fan, or we have heat exchange efficiency for a heat exchanger, or we have information on a cooling panel. Then we can go into detail and actually identify maybe what are the challenges, what are the reasons if we have a performance that is not as expected. And of course, depending on the level of detail of data, we can do different things. Typically, if we only have a billing level, we can say something about resource use and we can assess the performance of systems. While if we have a high level of data, we can both estimate performance, we can maybe do fault detection, we can maybe estimate resource use. So we have, of course, a lot more information available and also can do a much more detailed assessment. Then we are also evaluating when we are doing actual measurements and measuring the performance. We have different opportunities to make comparisons to evaluate what is the quality of this performance. We can compare it to, and maybe for some components they have an energy label. We can compare, does it fit with the energy label? Does it fit with what we expect of the actual use? So we can compare it with the actual conditions. Does it perform well? And we can maybe also compare it to historical data to see has the performance decreased or deteriorated during the last year. So we have included in our assessments different possibilities to make to compare with different kind of references to get different kinds of information. And finally, I'll just give a small example of one of the assessments that we have included in the library. This is the example. It's the performance of the rotary heat exchanger. On the left side, you can see the results of the heat exchange efficiency as a function of outdoor temperature. And of course, when it's cold outside, you are maybe using the heat exchanger very full efficient, and you reach a high level of heat exchange efficiency, and then as outdoor temperature increases, you don't have the same need for heat exchange efficiency. But on the right side, you can see in the evaluation of the performance. The red curve shows what is the useful heat recovery efficiency. So this means how much heat recovery do we actually need to decrease heating consumption, and of course also decrease cooling energy use. And when the outdoor temperature is cold, the black curve shows the actual heat recovery efficiency, and you can see in area number 1 that the actual performance is lower than what is useful. So this means we could actually, it would be beneficial to increase heat recovery efficiency. If this difference is big, we could consider, would it be beneficial actually to change the heat exchanger to another one which is more efficient? In this case, it's quite close, so probably it's not economical beneficial to make a replacement of the heat recovery wheel. In 2, you could see there's a good correspondence, and if you look at area number 3, you could see that the actual recovered heating energy is much higher than what is useful. So this means this here, the control of the rotary wheel is not optimum. We are recovering more heat than we need. This may result in increased temperatures in the spaces, or maybe an increased cooling need in some of the systems. So it's quite easy to identify here that we have some problems, and you can start identifying how can we solve these problems with just looking at such an overview curve like this. Thank you.
Thank you, Per. Our third speaker is my colleague Guilherme Graça, associate professor also at the Faculty of Sciences of the University of Lisbon.
Thanks. So Per presented, I don't know, was it the heart or the liver? I was a bit confused. I'm presenting maybe the legs, maybe the arms of the project, and in that sense, we are still struggling a little bit with our walking capabilities in this area. Pedro Ferreira did an overview of what SATO does, and Per presented the assessments. And then the idea is to use the platform as presented by Vinicius with the assessments, so the evaluations, the dynamic evaluations that Per presented briefly, to provide services. So that's, let's say, one of the jumps that we are delivering with this project is the capability of providing services to building owners and building users, where a service is a software unit that builds on the assessment capabilities to deliver a result and an added value. Within our framework of services, we have these areas that you see on the right, where the simplest service is on the lower right, the self-assessment, and it's a simple capability of displaying the results of the assessments. As we move upper on the right side, you see more complex services that provide optimization capabilities and are meant to improve building operations as a whole in different areas. Are system operation, flexibility capabilities of the building. In the upper level, we have, let's say, the main goal, which is to provide control systems that optimize different aspects of building operation and building systems. So, quite a complex task. The services that the SATO ecosystem hosts are shown here. You have the control services, the user comfort related services, building flexibility, and then towards the bottom we have a service that provides advice to building users, that's S51, and then S52 is the capability of the SATO system to deliver calibrated digital twin of the building. And I'll show a bit more about that, our capability on the digital twin side. The aggregated control services that we provide control, for instance, natural ventilation in combination with HVAC operation, lighting, shading within the constraints of user comfort. What you can see in this schematic is that the services have a continuous interaction with different assessments, where assessments here are named with A, so we have A21, 25, 31, these are different assessments from the large list that Per showed, and then the services, they get the results from the assessments and make decisions on system control. In this case, control of several different systems. One of the, in the short time that we have for this presentation, I'll just give you a bit more detail, a bit like what Per just did with the heat exchanger and the heat recovery. One of the services we've been working on is an aggregated control service that provides optimal operation of the cooling system of a large library, where the library has HVAC and natural ventilation. And the service uses several assessments and sensors, as discussed, and makes decisions on whether windows can be opened. The main challenge in a building with openable windows is not to decide when to close the windows. That's quite easy because it's getting hot. Let's say you're in the summer, and so clearly you need to close the windows and turn on the HVAC. That's quite an easy decision for any control system. The main struggle is to decide when can we open the windows and keep them open, because of course we could, in a given service building, open the windows and then say, oh, it's not good, let's close them and turn on the HVAC. So this key decision of these systems is, can we open the windows? Will it be a good decision that we can maintain for adequate amount of time, an hour, 2 hours, etc. Once we open the windows, we also need the capability of adjusting to maintain indoor conditions within the same range as HVAC. Of course, because we open the windows, we do not become entitled to have, let's say, warmer buildings and comfortable. That's not really competitive with HVAC. We need to open the windows and have similar conditions. That's what we've been doing in one of the pilots of SATO. So we've been deploying the aggregated control system, and we have been also measuring the energy savings that this system can deliver in different outdoor conditions, where when you see there maximum outdoor air enthalpy, so these are comparable days of weather. On the left, you have different days where we use different strategies in the summer in our libraries. So the dark is the energy consumption for cooling of just keeping the HVAC on. The green is, you see a reduction of 70% in a milder day and 30% on a warmer day on the right of using SATO to control the window opening. Then the blue is as you add nighttime cooling. So nighttime cooling can provide many more energy savings, but more on milder weather than on very warm weather. On the right, when you go to a warmer day, about 30 degrees outdoors, maximum temperature, you get a warmer evening, so the system saturates. These measurements were done, of course, using the SATO platform to acquire the data, and using our aggregated control system to make the decisions. Moving on to a little bit detail about other systems, we also have a service to maintain user comfort. We also have a service that focuses on indoor air quality, mostly by measuring CO2 levels and making decisions on outdoor airflow. We also have lighting and shading control. In some of our pilots, we have automated shading, like a retail pilot that Frederico will show later. That would be the Portuguese Frederico. Then we have a flexibility control service that optimizes building flexibility capabilities to meet grid demands. This service uses building as a battery, so thermal mass, as a source of flexibility. We'll show a bit more about that later. And is able to, as a service in a given building, optimize the deployment of different rooms to create virtual batteries. So the next slide gives you a better perspective. So although it's a bit hard to understand, the idea is in a building you have different rooms that have different capabilities of reducing energy demand by turning off their HVACs. In the top right you see the schematic. And then by turning on and off different rooms during the day, this is time, we are able to deliver a continuous demand reduction of the building, so a continuous battery effect obtained from the thermal mass. We also have a very simple service to control energy systems, and finally, this is something I'll be showing later this morning. We use the assessments and the beam capabilities of SATO to deploy self-calibrated digital twins. So let's say simulation models that are accurate and can be used for different purposes, in particular optimization. Thank you very much.
Thank you, Guilherme. We move to our last presentation in the first part of the workshop, and we have with us two of our colleagues, my colleague from the Faculty of Sciences of the University of Lisbon, Manuel Fonseca, and then Pablo Gilabert from SAIPE, a Spanish company that works on many things, but let's say on our project, he brought the beam technology to our developments. So, who is first? Okay, Pablo.
Well, thank you very much. Well, if previously we were talking about the heart, I know it's important having a good heart, and maybe it's important having legs. But maybe the most important thing is how you look. So this is what we are going to try to explain here is the skin, let's say. And well, in this case, we have like two main products the OpenBean SATO and the SATO web application, and we will try to summarize the main functionalities of these two applications. So let's start with the SATO web app, and Manuel will be in charge of this.
So this SATO web app is one of the faces, if you want, of the SATO. It is provided in a web version and also in a mobile version of the application, so you can use both of them. It was developed using what we call a user-centered methodology. So we started with the requirements from the beginning of the project, where we identified the actors and the needs that they have. And then we created several versions of the prototype and of the application, starting from non-functional prototypes at the beginning and finishing with the final application. And between each of these versions of the prototypes, we performed tests with users, we collected feedback, and we improved the application. So we did it during the overall project. In terms of the connection of the face with the rest of the body, as you can see on your right is the user interface. We use some technologies like Meteor, JS, and React for implementing the user interface. And then all of this is connected with the SATO platform, where we get access to the data, assessments, sensors, all the information that is provided by the platform. And now I give you just a short overview of what is provided by the application in terms of functionalities. So the application allows the users to get an overview of the buildings. We can get an overview of, for instance, the weather at each building. We can get an overview of the comfort of the building in terms of temperature, humidity, CO2. We can also get an overview of the assessments, and each building has its own set of assessments. We can also get an overview of the consumption, year, the daily consumption, monthly, or even for the year. So when we get into a building, we get a quick overview of everything. We also provide access to real data from sensors. And here we can see, for instance, in more detail, the monthly consumption. We can get into a specific room and get information about a specific sensor and see the values for, in this case, for a CO2 sensor. And we can see the values for the last, I'm not sure if you can see it, last 24 hours, for the day, for the month, for the year, so we can get. You believe me? Okay, that is good. The application also allows the user to provide feedback about comfort, and here we have 4 dimensions that we can provide feedback. One is about temperature, light, noise, and air quality. And besides providing feedback, we can also see the overall feedback provided by the users, and with that we can get a quick overview about the comfort of the building. So if we have a lot of feedback related to noise, we can see that something is not very good, so we need to be aware. The other functionalities that we integrated in the application is the assessments. And overall, we have more than 20 assessments already available in the, in the web application. And the values that we are showing are being computed in real time. And we get, with the assessments, you can get an overview of the assessments per building. So we can see for a building the status of each assessment, so the actual value for each assessment. And we can also get detailed information for each of the assessments that are provided in the application. So here is an example of the overall for the assessment. So for the school library, we can see the different assessments associated to this building, and we can get a quick overview of it. On the right, we have for the Aalborg University. So as you can see, maybe not, the assessments on one building and on the other are different because of the buildings have different assessments associated. And finally, we can see details about the assessments. Here is one assessment about the whole building energy. These are the values for a year. We have the value that is being spent and the reference. So we are below the reference, so it means that is good. So it's the assessment provides this. We also have an assessment for the thermal comfort. Green is on the spotlight, and red is hot. So we can get a quick overview. More assessments. This one is about the smart readiness indicator. We have another one for the air quality, and the last one about the boiler. And finally, one for the Aalborg University that is related with the air handling unit fault. And so we can get information about in what conditions there was a fault in the air handling unit. So to conclude, the SATO web application enables real-time energy monitoring and management, and also the optimization across different buildings. And we do that by offering customizable assessment tools and feedback mechanisms so that users can optimize the energy and improve the comfort. It was developed using a centric design, so it means that we put the focus on the users and the usability.
So I'm going to describe this other application, OpenBeam SATO. And I think the best way to understand the main functionalities of this application is with a video. Let's see if it works. Yeah. So this is the application. We can import BIM models working with IFC formats. Here we have the possibility to locate the different sensors, and there is a layer that verifies that the sensors have been defined in the right location according to some specific rules, like the minimum height, maximum height, distance from facades, etc. And then we have this other feature, which is representing the results of the sensors and the assessments. In this case, we can select, okay, I want to visualize the results of the CO2 sensors or the temperature sensors, and we can even control the contour plots in order to, highlight the specific results that we should control. And then we have implemented in the last iteration the possibility of displaying these results of the assessments. So with just one look of the 3D model, we can obtain the results of the real performance. No? We have done it for air quality, thermal comfort, and also occupancy. And then we have been researching about the possibility of moving all this data to your mobile phone. And we have applied it in a new technology. Well, it's not new, but it's quite interesting, which is augmented reality. So any single occupant can display in their own mobile phone the possibility of representing the real data, the real results of the different assessments, identified or sensors. So this is the architecture, how the data is moving. We have two main data sources. One is the SATO platform, and then the other one is BIM Server Center. So from one source, we get all this information related to the real performance of the building, and from the other, the data coming from related to the BIM, the geometry. And then we have been working on creating a connection, working with IDs of the buildings, ID of the rooms, of the spaces, of the different zones, in order to create the connection. No? Then, in the first iteration, we built this sensors location results. We consider it quite important, as we are working with BIM models, creating some functionalities for the architects or the engineers that are in charge of defining where should we locate the different sensors. With some basic rules, and we can control, okay, let's put a sensor of temperature here, humidity here, CO2 here, and we can even control the interaction with the other elements of the buildings. So in this case, we can see we have created like some minimum volumes in order to avoid in displaying one sensor close to the air conditioning, for instance. Here again, we can represent the results of the different sensors of one room. And then this last part is about representing the assessments. So we have the legend, which is different for each one, and we can represent these final results. And the last approach is, okay, how can we display this data in augmented reality? So it's quite interesting because now the occupants could be part of the system. This is the general workflow. So generally we create a BIM model, we import it, we define the rules we want to apply, then we control the data coming from the building, and we represent this information. We can identify two main products, let's say. One is focused on the design phase, and the other is focused on operational phase. So we can, let's say, sell it to different stakeholders. No? On the one hand, the designers, architects, engineers, but also the people in charge of the behavior of the building, of the performance, no? Like facility building managers and building owners. And that's all. Thank you.
Okay, thank you, Pablo. So this ends the presentation cycle for part one of this workshop. We can take a few questions from the audience or from those that are online. So if you have any question, please go ahead now. And okay, any more questions?
Right. But I wonder if you've thought a bit also with Manuel, whether people want to be bothered with interacting with any complexity. I think that's a challenge, no matter how good it looks.
Well, I totally agree. I think one of our main challenges is making it simple. So trying to represent really complex formulas you have been applied in these old assessments in a basic way with colors graphically easy to understand. I think it's the way to arrive to most of the people, because it's true that understanding and trying to understand all this data, it's quite complex. Then on top of that, we can even build some recommendations. So we have all this data, so we recommend you to do this or to do this in order to, okay, I just need to read one sentence and that's all. And I think it's important to have in mind.
So I agree with you, and basically when we did the user-centered design and all the steps that we went through the iterative design, we went to the users and we tried to simplify everything. Even with the representations for the assessments, we tried to give the information right now. So when people look, they can see that something is not well, out where they can improve or they can change it. The actions that they can do.
So I just have a comment to that, because I'm sure people will not look at this continuously. They will only look at it when they feel they have a problem. Then they will take a look, and then they have the opportunity to see, is this problem only for me in my room, or is it a general for the building? Because if it's only for one room, then maybe you need to do something in your space. But if it's a general for part of the building, you need to contact the manager and say, we have a general problem here you need to solve. So I think it's more a help to understand when there is a problem, and not all the time. So hopefully they will never have to look.
We have another question.
To ask what was the profile of the test persons you involved in the testing? Is that was single occupants or managers in what was this structure of test persons?
Indeed, when we started with the requirements where we get information from different actors like occupants or building managers, evaluations we did the same. So we involved different types of feedback for each of the functionalities, because there are some that are for occupants, but there are others that are more specific.
Any more questions? If not, then we will proceed to the second part of our workshop, which is looking a bit more in depth to some of the innovations, let's say developments that we think are innovative in the project. And I think given the delay that we had at the beginning because of the technical problems in the room system, I think we will shift the second presentation that we would have in this morning for after the coffee break, and then we manage the time on the panel discussion that we have at the end. I think that's the best strategy to keep up with the coffee break timings that we have here. So our next speaker, continuing with the analogies to the human body, I think is going to give us a bit more detail about, let's say, the coordination or the automating and coordinating all the computational processes that we have to execute to make the whole system work. So we'll have now with us a PhD student in our Faculty of Sciences of the University of Lisbon. It's Aniakor, that will present our work on interoperability and context awareness for our systems.
Good morning, everyone. First of all, I want to say it's a good day to motivate myself. So I will spin off from where Professor Vinicius, who is my supervisor, left off. This is part of the work developed within the SATO project, and the title is Interoperability and Context Awareness for Smart Buildings Autonomous Energy Management. To begin, I would like to start off with some basic stats on the SATO platform. The SATO has 9 pilots, and within these 9 pilots we have over 80 plus buildings, and each of these buildings we have different types such as residential, education, and office buildings. And within those buildings we have over 450 zones and spaces. And within those zones and spaces we have over 3,300 devices. Going further, each of these buildings have different devices that are being manufactured by different vendors, such as Excel, Siemens, Shelly, and Ready. And these proves challenge or pose challenge towards integrating the data from these devices as they are heterogeneous in nature. So one of the primal challenges we faced was to actually to build a data model that can represent these devices in a homogeneous way. So going further, we had our primary objective. The primary objective was to facilitate a seamless data and system integration through semantic-based approach. And the other is to be able to leverage the semantic richness to enable automated discovery of assessments and services, which I'm going to expound on later. So what to do? The first step is to represent this data and semantics in a standardized manner. First step. Then also to create a knowledge base to reflect the highly connected knowledge of the platform. And the third thing is to be able to track the historical data coming from the census. Going further, what are the technologies we decided to use? I will just briefly mention them and explain later. We used ontologies, smart data models, and the new generation service interface link data. And to represent the highly connected knowledge, we developed our context information model. And to track historical data, we incorporated the use of time series database. Now, talking about standardization, we adopted semantic web technologies such as using a common approach, which is ontologies, as they serve as a formal and explicit representation of conceptualization within a domain. And they make use of this linked data approach, which comes in the form of triples, subject, predicate, and object. And building on top of that, we decided to leverage the new generation service linked data interface to be able to provide a digital representation, of physical entities within the building. Because in a way that they can identify entities using URL and URN. And also, this NGSI LD, they enable us to be able to combine multiple ontologies. And by that said, we adopted to use smart data models, not to reinvent the wheel, but to leverage what is already existing there to define our concepts. So concepts relating to building spaces and devices, we adopted the smart data model. However, at that time, there were no definitions for zones. And in SATO, we had the concept of zone, which is a virtual space that can be used to perform assessment. It can be within a space, or it can be a collection of spaces where an assessment can be performed. Going forward, with this, we have our context information model. As Professor Per mentioned, he has the heart, and Paulo mentioned he has the skin. Brain of the platform. I'll say this is the brain of the platform, as it serves as a knowledge base, connecting and showing how everything within the platform are being connected. Further, I explained this, we just use a historical database like timescale DB to capture the sensor information, the dynamic data within the platform. So in SATO, we intend to create context-aware applications like intelligent systems that can adapt its functionality based on the context of the building. One scenario is user comfort, which implies the convenience of the user. I want to introduce the concept of tasks. What we want to do is to introduce the concept of tasks, show how tasks are involved within certain spaces, zone, and on a device level. Also create task definition, integrate them within the context information model, and also leverage this knowledge base to be able to create an autonomous task instances. These stuffs here are foggy now. I'll try to break it down in the subsequent slide. A scenario of one context-aware application, thermal comfort. We have an occupant in a room, and he has his convenient temperature bandwidth. We have a temperature sensor there, measuring the temperature. Then, if the temperature falls outside the bandwidth of the convenient temperature, it triggers a service, such as maybe a command, is a service that sends a command to the actuator to open the window and so on. The message I'm trying to pass here is that with this kind of application, there are different computations that are performed. And in these computations, there are dependencies on them. Maybe for the service to be triggered, one computation needs to be performed, such as so with that said, the core of SATO is not just for building monitoring purposes, but to assess building performance. And assessing this building performance has several layers of computations that depend on each other. So we decided to, we created this philosophical intuition of tasks. Help us discover tasks that are associated with the platform. Idea of task, I'll give a brief definition of what task means. The idea is any computation or logic that gets information from the context information model, computes that information, and publishes that information back into the context information model. So, in our application, tasks can comprise of one or four categories, which are virtual sensors. Virtual sensors can be simple calculations. We have the KPI, which computes new metrics. KPI compare with some baselines to give a report. And we have the service, which acts on based on the other layers. Now, when it comes to modeling tasks, there are several properties in tasks, but tasks have three main properties. One, based on how we all agreed to model what task is. We have the entry point. The entry point points to a function to execute that task. We have requires. Requires means what is required for a task to actually run. Then we have the frequency, which is when it should run. Going further, we have the task. We created the task definition, which is like a generic template. It's not under the context of any. We have a task thermal comfort, but the task instance is actually instantiated under the context of the building. So for thermal comfort, we have this task can be instantiated in what is required. In the generic template, it shows it requires a temperature sensor. Task instance, it instantiates it with the ID of that particular sensor. And also, the entry point is the same. And also, the frequency, you can decide to choose when to, the periodicity when to run this task. Now, we have the component, which is self-assessment framework. Here, we have several task instances that needs to be deployed. So the idea of the self-assessment framework is to actually schedule the execution of this task based on the property required. And I will explain. For example, starting, we have different sensors. Then we have the virtual sensor, which is one of the fundamental basic level of a task. It computes the average. Going further, from the average, it can be used, this information from the virtual sensor can be used to the KPI can be used to give a However, there's still a major challenge in the sense that tasks, have a major challenge in the sense that there are tasks that can be deployed in multiple spaces. For example, thermal comfort. The generic template is we need temperature and occupancy for us to instantiate this task. So now we imagine this as a building with 9 spaces. So it goes to the first space, checks, what do I need to launch this thermal comfort task? I need a temperature sensor and I need an occupancy sensor. Those information are provided there. Yes, it's good. We can launch the task. It goes to the second one. Oh, it has only one temperature sensor. It doesn't have an occupancy sensor. No. But with this approach, it's a tedious approach because we need to always be checking all the building spaces to see if the task can be actually launched. So we decided to create a component which is called the self-discovery component, which will look at the task definition and autonomously it will be able to identify all the task instances that can be deployed within the building. That is the idea of the self-discovery. And to recapitulate or to conclude my presentation, I talked about how semantic web technologies can be used to standardize and provide homogeneity between device and concepts. Then we introduced a novel concept titled known as tasks in the SATO platform to support self-discovery and autonomous execution of tasks. I know that in this presentation, I was just using just one example. Thank you very much.
Thank you, Mirko, for this introduction to the computational foundations for the coordination of the self-assessment and optimization processes that we have. I think I can take questions now from Mirko, and then afterwards we will take questions for the other presentations that we'll have for part 2. So if anyone here on the audience or in the online session, please go ahead. We have one question here.
So, Miracle, thanks for the very clear presentation. This self-discovery component, I think, is one of the most interesting aspects of the work. Could you just provide better, like an example of how this thing operates and how the self-discovery occurs?
So basically, yeah, it is not yet fully developed. It's an idea, but the simple approach is we are using heuristics, just basic logical rules. Certain entities are present based on requirements we should launch. But however, based on the knowledge base, the context information model, more advanced technique can be used to discover these task distances, which we intend to look at, such as leveraging graphical neural networks and seeing how they can be used to discover new tasks using relationships.
Okay, I think first I would just complement the previous answer, is that the context information model has all those required relationships. So we created the default registration of what those tasks need. And then for each building, we start looking for, okay, for this building, let's see the requires, what can I fulfill? And if I fulfill all those requirements for a room, for a space, for a building, a whole building, and so on, when we fulfill those required relationships, we launch these tasks autonomously. So this is the idea. We have this context information model ready for that, helping. We just need to search for the requires relationships and see which are fulfilled and launch the tasks. That's it. Yeah. I mean, the idea is we can launch all assessments that are possible. What is adequate or what are more important or so is more related with services later. We can advise or we can autonomously actuate depending on the usage. And no, not yet. No.
I actually going to complement a little bit this answer, because and it's about the importance of the beam and the beam file. If we have adequate and appropriate beam files that have the necessary layers specifying where the sensors are, the definitions of zones and everything, and this is the general idea in SATO, is that we ingest this beam file and we populate this context information model with all already these devices and the definitions of the zones, and then it starts creating what are the assessments that are possible, what are the... But this is an automated process that can start with information from well-prepared beam files that can actually be the first setup of the platform. It's parsing the beam file, looking for the right layers. And then the self-discovery. No, it's logic. It's much simpler than ChatGPT.
Just another interesting aspect of this discovery aspect is that, as Pedro was explaining, we can create the tasks without only with Beam, and start creating the tasks that we can complete now. But at the same time, it helps also on destroying tasks that are not possible anymore. So it also, if there is any fault in any sensor or you stop receiving data, it autonomously can detect that and stop processing that part, or launch some, trigger some log or some registration record, say, okay, there is a problem here in this sensor, we are not calculating anymore this task, until eventually we revise the building from time to time and then launch again when it's back. So it's kind of autonomous fault detection and recovery that also enables or disables tasks associated with these faulty sensors as well. So it's, everything is related to autonomous here. Yeah.
It's the self, yes, that's true.
Basically, since we have the context information model, we can detect when was the last time we received data, and when we received this data is about when it was observed. So we can use this information to say, okay, I can reinstantiate the tasks because I am receiving, or I stop it and it does not make sense to continue processing data that are already processed. So this type of things can be done. For that, we have in the middleware part, we have some parts that deals with data quality. So it's outside of the scope of the discovery. The discovery just check if it's receiving data or not to launch the tasks. But we have in the data pre-processing part, data quality checks that can annotate the data that we are receiving. So when put the data in the correct model, harmonized models, we also annotate that saying, okay, this is out of the range that was supposed or so. So it's an enriched data set already refined. Yeah.
Any more questions? All right. No more questions? Okay, then we stop or pause the workshop for now. We resume at 11 when the coffee break ends. 11. Half an hour, yes. That's according to the conference schedule.